Okay, I guess we can go ahead and start the class. We finished the introduction chapter last week. We are going to start chapter 2 essentially, which is going to focus on conduction heat transfer.
Is that in the second book? Or
It is the second book, yeah. It is. We are not going to use the first book anymore. That's just for the first part of the first chapter of the class. So conduction heat transfer, we are going to start with whatever you have learned in your undergraduate heat transfer, like one-dimensional heat transfer, fins, all of those nice things, thermal resistance method. Let me write them down here. 1D heat transfer. And thermal resistance and fins, which I assume we can cover all of these three topics today if you're fast enough. But again, the assumption is you have learned all of these in your undergraduate heat transfer, and this is just a review, right? If you don't remember any of them, or if you had a question during the lecture, make sure to ask. And then we will move on to multi-dimensional conduction. Which we don't cover as a part of undergraduate heat transfer in this university. But there are other universities who do cover multi-dimensional conduction as in their undergraduate curriculum, right? But we don't. So this is for those of you who graduated from here. These all will be new. Who graduated from this university? And who did you have your heat transfer with? Chenley. Okay, yeah. He doesn't go over multi-dimensional conduction. And then we are going to use the separation of variables method to solve a two-dimensional conduction problem, which is essentially, this is part of the multi-dimensional. We will move on to transient conduction, and we will talk about the lumped capacitance method, which is also part of the undergraduate curriculum here. Capacitance. And we will talk about the two-dimensional or multi-dimensional, essentially 1D transient conduction a little bit, and try to solve the partial differential equations of transient conduction. If we have enough time, we will move on to the porous media analysis and the bioconduction. And then we will do a little bit of microscale conduction, which will be very similar to what we did in chapter 1. So we are just going to glance over it again. Think of this as a review of chapter 1. Sure. These are just a topic, so nothing special. So, are we good? Okay. So, let's talk about one-dimensional conduction first. And here we are going to derive the heat equation that governs the conduction heat transfer, which is essentially the main partial differential equation that governs the conduction heat transfer. In this, it is obvious from the name, it is a conduction heat transfer equation, so we are not going to see any convection and radiation or any other modes of heat transfer with this equation. So keep that in mind. If you were to write a program that is supposedly capable of solving the heat equation, that program won't be able to see convection heat transfer, right? So you need to keep, or if you were to solve this on the solution of this equation that we are going to see later in just a bit, won't be able to handle convection heat transfer. You have to keep that in mind, right? Or radiation. There are methods that we can actually incorporate convection, simple convection in this equation, but the equation itself won't be able to solve the convection heat transfer. So again, the goal here is to start by the general heat equation, and then we'll move on to the one-dimensional heat equation. So where should we start? Whenever you want to find a governing equation in heat transfer, you have to start with an energy balance. That's always the game. That's always the case. But essentially, a heat equation, any type of heat equation, is a simplified form of an energy equation. An energy equation can be derived from energy balance. So let's look at this simple case. We have a solid block with insulation at the top and the bottom. Okay. And we have some heat, we have temperature difference, of course, from these two sides, which essentially means that we have heat energy moving from T1 to T2. So we have some sort of a heat transfer here happening here. The first thing I want you to answer is that what is the type of heat transfer? What is the mode of heat transfer present?
Sensible?
It is sensible. Of course, it is sensible heat transfer. But since it's a heat transfer inside a solid material, it is conduction. How many dimensions are present here? Let's take a vote. 2 or 1 or 3 or maybe 0. 2. Who goes for 2? Okay. And I guess we have some whole lots, so I want to hear from the whole lots. Why is it not a two-dimensional heat transfer? From those of you who didn't vote for a two-dimensional heat transfer. Yes. John.
I was going to say because T1 and T2, the difference is only horizontal. There's no difference in the vertical direction in terms of temperature.
I'm gonna switch to that, but also say that the way you've written that implies that into the page is still T1 on the left and T2 on the right.
Yeah, I mean, that is true. The way I've written it gives out the point. But so, well, how can we make sure it is a one-dimensional heat transfer? It is not two-dimensional. Why is this the case? It is because we have insulation. So there is no heat transfer from these sides, right? Which is essentially going to force a uniform temperature boundary at these two locations. So the only heat transfer you're going to see is from this to this. It is not a complete one-dimensional, but it can be a quasi 1D heat transfer or heat conduction. So let's write the energy balance for a small element of this solid block. Do we have any questions? Do we understand why is this a one-dimensional heat transfer? No? Okay, where's the question? Why don't you understand this?
No, sir, I meant
Oh, you don't have any question?
Yeah.
Okay. Okay, so let's take a small element of the surface. And which essentially is a control volume, right? And let's write the energy balance for this small control volume. If you recall from the previous lecture, energy inside the control volume is equals to energy in minus energy out plus the energy generated. And you have to keep in mind that E dot is essentially the rate of change of energy. So E dot is a derivative of energy with respect to time. It is not just total energy. You just have to keep that in mind. Okay, so we have the energy balance. So the first thing you want to do is to come to the boundaries of this problem. Which we have 4 boundaries. 1, 2, 3, 4. There is no heat coming in or going out from the insulated surfaces, right? That's the definition of insulation. So we are only going to have some heat in and heat out from here. Let's say heat coming in is heat flux multiplied by the cross-sectional area. Okay? And heat going out is going to be the same heat flux multiplied by the cross-sectional area plus the changes of that heat flux multiplied by area multiplied by the length of this element.
What's the subscript you have next to the Q?
Q of x, so Q in the x direction. It is Q double prime of x. So, again, let me actually magnify this here, the control volume. This is the control volume. What I'm saying is that we have Q double prime x multiplied by the cross-sectional area here, and then energy going out is going to be the same energy plus changes inside the control volume, right? Does it make sense? Okay. And how can we characterize the changes inside the control volume? Mathematically, changes of heat flux with respect to x multiplied by dx. Or let's call this delta x because we don't want to cancel. The length of this control volume. And inside of this control volume, we may have some energy generated. Okay? So, E dot of this control volume, changes of energy inside the total changes of energy inside the control volume is equals to E dot in, which is Q dot prime of x multiplied by the cross-sectional area minus Q dot double prime area, this is E dot out, plus the changes. And plus the energy generated. Energy generated, we are going to assume that is equals to heat generation, Q prime, multiplied by the volume of this control volume, right? This cross-sectional area multiplied by this is the area, cross-sectional area, multiplied by the dx, which is the length of this control volume. And this is also, keep in mind, this is also ds, dx. I just wanted to make sure that you are not canceling these two with each other. That's why I changed it to delta x. But in reality, it should be dx.
What is EG again? Is that a Q dot A dx?
Yes, Q dot is the heat source. That's a volumetric heat source. So amount of heat generation at each point, right? And we want the total of that. So if you have a value at each point and it is uniformly distributed, you have to multiply it by the volume of your system, right? To get the total generation. Does it make sense? I have the value at one point. I have to multiply it by the volume. And that's what we have done. So this is going to be equal to Q dot A dx. Okay, and let's change this back to dx. Again, you shouldn't really cancel each other, these two out with each other. One question before moving forward. And whoever answers this question will definitely get a bonus point. How did we come up with this parameter? Again, I said, and there is a mathematical explanation for this. It is not a physical explanation. It is a mathematical explanation, right? Yes.
So it should be because of heat gradient, because of delta F.
Yes, that's what I said, right? But that is not a mathematical explanation. I'm looking for a mathematical explanation. So for a I said let's assume that this is the changes of heat gradient, the heat flux at that location, right? And that is an acceptable assumption. We can definitely, yes.
This is the heat rate?
A mathematical explanation. So I have the value of, let's go back to this. I have the value of heat rate at this location. I want to find the value of heat rate at this location.
Is it extrapolation?
Extrapolation, no. No and yes, but no.
You mean like purely mathematical from like all the way back to like definition of like a derivative?
I mean, not all the way back to the definition of derivatives, but all the way back to like calculus 1 and 2 in university, yes.
This is like one of those numerical methods that you have the initial value and like the forward point difference.
You are getting warmer.
Difference method.
You are getting warmer.
Thank you.
Scroll up a the entrance and this QXA can be cancelled out with each other. And when we substitute conduction heat transfer on QX second, therefore we cancel.
No, that's not what I'm looking for. So I'm only looking for finding the value at this point based on the value at this point. Right? It doesn't have anything to do with the equation we have up here.
That is the difference method, right? If you know the initial value and
Yes.
That term represents how heat changes at every value of x.
It's like a,
I'm gonna go with Mohammed's answer. So I was looking for this first order Taylor series. So what did first order Taylor series tell us? It said that if you're looking at the value of a function at point x plus a, the value is equals to f of x, value at point x. What was the rest of it? Derivative of f, right, with respect to x, multiplied by the distance between the two, a, divided by the factorial, right, of the order. So here it is going to be 1 factorial, plus then the second derivative divided by 2 factorial, ax squared, and plus O of an, right, something like this. So we are essentially, the value at this location is mathematically the answer to the Taylor series expansion, right? The first order Taylor series. The reason I brought this up is because I wanted to just refresh your memories on the mathematics, because we are going to deal with a lot of mathematics. Okay, so this essentially means that the value of heat flux at this location is going to be Q double prime plus the changes, which is the derivative multiplied by the distance, which is dx, divided by 1 factorial, which is 1, right? Okay. So we have this. And you will get the bonus one. Just send me an email, a reminder email. and the closest answer. Okay. Do we understand this? Do we remember the Taylor series expansions? Okay, that's good. And we are going to come back to Taylor series expansions at the final chapter of the book when we are talking about the finite difference method. Do we have anyone in class who is familiar with finite difference method? Yes, we have a couple of people. Okay. It's a numerical method, and we will get to it. Okay, so we actually have the right-hand side of the equation completely figured out. Let's go back to the left-hand side of the equation. How can we find the energy generated or the total heat rate? That's a better way to put it. What is the total heat rate inside this control volume? Yes. Rho CV delta T, exactly. So rho CP, right? Delta T. That is the Q, but we are looking for the rate of changes of this value. So dQ dt. The only parameter that is changing here is T. So this becomes rho Cp dt dt. And this is also talking about the heat rate at one point. We are looking at the total heat rate over the volume of the control volume. So we have to multiply this by the cross-sectional area multiplied by dx. Does this make sense? Okay. So let me rewrite this up here. Rho Cp dx adx dt dt.
So dx again, that delta x, the width of the
This is the width. Yeah, this is the width. This is not the derivative. Whenever you don't see the a dx in a denominator, it is not a derivative. It's just a width. Okay. So let's rewrite this. Let's simplify things we can. dx dt dt equals to these two will cancel out. We're gonna get negative d dx of q double prime a dx plus q dot a dx. What else can we take out here? ADX. If cross-sectional area is constant. That's a very important point, right? If the cross-sectional area is constant, we can take the ADX out. If not, we can only take the DX out. So we'll end up with this rho Cp dt dt negative ddx qx plus q dots. And if you recall, Fourier's law tells us that a heat flux is negative k dt dx. But we need to make an adjustment here, because temperature is changing as a function of your location, x, as well as your time, t. So it is a temporal and a spatial change, both of them. And an absolute derivative is a wrong way of talking about the changes of temperature. So we have to change to a partial derivative, right? So let me rewrite this again. We're going to get rho Cp partial t equal to d dx of negative k dt this is a partial again, partial t partial x plus q dot. If your conductivity is constant, we can take the conductivity out and negative signs will cancel out. We're going to have rho Cp partial t equals to k partial squared t partial x squared plus q prime. This is your one-dimensional heat equation. Do we have, yes,
What's to the left of the ddx on the top equation?
k.
The one above that.
This was a negative sign, negative k partial x. And parentheses, so this is ddx of negative k partial t partial x, okay? Can we solve this equation? Any ideas?
Separation of variables.
That's one method, right? So we are here to solve these type of equations, right? Which means that it is solvable. Sometimes, not always. Sometimes. Okay. What is, yes?
So you also need boundary conditions.
That's what I wanted to get to next. So what do we need to solve these type of equations? We need boundary conditions, right? How many boundary conditions do we need for this specific equation? Is it just a one enough? Yes. 4. We have Muhammad, right? Muhammad is voting for 4. Anyone else?
Yeah, I'll go with 4, 2 for time.
Why do you need 2 for time, 2 for x?
So for 1B is going to be two boundary conditions, and maybe one initial condition.
So you change your answer to 2.
Yeah,
Okay, we have 2, we have 1, 2, 1, 4. I want to hear from the rest of you as well. 2. Okay.
Yeah, I was gonna say 2 as well.
I guess we have some sort of a consensus on 2, right? Do you have any dissenting voice? Other than 3, okay. Why 3? 1 for time, 2 for space. How do we figure this out? You have the first derivative of time, which means that you only need one boundary condition for time, which is called initial condition, right? We don't really call that time boundary condition, we call it initial condition. So we need one initial condition here, and we have a second derivative of x, which means that we need 2 boundary conditions here. A total of 3 boundary conditions. What if this problem was a 2-dimensional steady state heat equation, heat transfer? How many boundary conditions would we need then? 4. A steady state, right? A steady state means that it is not time dependent. So the time dependence is gone here. And we will come back to actually that part later. So the initial condition part is pretty easy to understand. We are only going to get the time, temperature at any location at x, any location, and time 0. Then T of I. The boundary conditions are going to be a little more, we are going to have options. The first options we have is a Dirichlet boundary condition. A Dirichlet boundary condition is the same as the initial condition, a surface temperature. So temperature at a specified x, sometimes 0, sometimes whatever, any length, and any time is T1. Which essentially, think about it this way. Let's say you have a rod one end of that rod is held at a constant, is put inside a furnace and is held at a constant temperature. This is your Dirichlet boundary condition, right? And for initial condition, think about it this way. You start heating a rod from a certain temperature, and that certain temperature is whatever, right? 273 Kelvin, right? Okay? Next type of boundary conditions is called the Newman's boundary condition. A Newman boundary condition is a gradient boundary condition. So essentially a heat flux or temperature gradient is specified as at a boundary at any location. So partial T, partial X at any location, let's say at X equals to L, is equals to some value. Let's call it A, value A. What is the dimensions of partial T, partial X? Per unit length, that's the dimension. Kelvin per meters, right? And this is Kelvin. And then the third type of boundary condition is called the Robin boundary condition, which is essentially the same as the second one with a small twist. This is a convection boundary condition, which tells us the heat flux at a specified location, let's call it X equals to 0, is equals to the convection of the wall. Let's say you're talking about a building's wall that is exposed to winter winds, right? A convection boundary condition. Okay? How do we calculate convection heat transfer? H T minus T infinity equals to negative K partial T partial X at that specific location, whatever it is, X sub 0. So we are going to get three different types of boundary conditions. Any questions so far? This is the one-dimensional heat equation. It usually takes me 2 lectures to derive this for undergraduate students, which is, I mean, it's good that you're doing it in this class that is going to take us like 20 minutes. And you all follow, hopefully. Okay. So let's try to simplify this problem. And start from the bottom and build up on top of it, right? The simplest cases and move from there. The most simple case, the conduction case, is a steady state one-dimensional conduction. A steady state means that there is no changes with time. So partial T is 0. And one-dimensional, we only have partial T partial X, which is essentially something like this. Let's say you have 2 sides of a wall, and this is an infinite wall. What is the meaning of infinite wall? What do you think when I tell you that this wall is an infinite wall?
I don't know the actual distance between the two.
Can you?
Distance between the two walls.
There are no distance between the 2 walls?
Yeah, it is infinite.
No.
A wall that the length is very big compared to the width.
So exactly. So that's it. The width of the wall is much smaller than the length of the wall. If this is the length, let's say you have a door. A door is a very good example of an infinite wall when you're talking about the middle of the door, not the boundaries of it, right? So the length is usually I mean the height, whatever you want to call it, is like 2 meters, but the width is like 5 centimeters, right? It's much larger. So what can we say? What can we assume when we have an infinite wall condition? We can safely assume that we have 1D heat transfer. Heat transfer only goes from one point of the wall to this other point. Why is that this is the case? It is because we can safely assume that one side of the wall has a uniform T1 temperature and the other side has a uniform T2 temperature. And since the heat transfer wants to take the smallest distance to transfer the heat, it won't go from this location to this location. It will go to this location to the closest, from this location to the closest, this location to the closest, and so on and so forth. So we are only going to have a one-dimensional heat transfer. So let's rewrite the energy equation. Rho Cp partial T partial T, and there is no heat generation. No heat gen. That's actually the very important part of it. There is no heat generation in this part of our analysis. Okay, so rho Cp partial T is equals to K partial square T plus partial T square plus and let's write it with the Q. Partial Q partial X plus Q. Heat generation is 0. Changes with time is 0. And partial Q partial X is equals to 0. We can take the integral once, and this is essentially going to give us the Fourier's law, which tells us Q, total heat convection, not the heat flux. Total heat conduction is negative Ka T2 minus T1 divided by the L. And L here, let me actually change this to height, this to L, to avoid any confusions. L here is the width of the wall. One-dimensional heat transfer.
L is the width of the wall?
Yeah, I mean, your book has this as the width of the wall. That's why it changed W to L, right? Just to avoid any confusions later. Okay. Let's look at a wall that has two different materials in it. So this part of it is exposed to T1. This part of it is exposed to T2. How would you characterize heat transfer inside this wall? Let's call this T3. We have T1 and T3. The length is L1 and L2. How would you find the total heat rate inside this wall?
You can calculate between T1 and T2.
You can
T2 is the
temperature here in the middle.
yes.
Okay, so Q is going to be Q from 1 to 2 plus Q from 2 to 3. Is that what you're saying? Yes. Which essentially means that Q is going to be negative K. Let's bring this negative sign inside this, since we are dealing with this linear case. So let's rewrite this as T1 minus T2 divided by L. Okay, just to have a positive sign. So it's going to be negative K, and this is K1, K2. K1 multiplied by the area, T1 minus T2 divided by L1, right? Plus K1 area, T2 minus T3 divided by L2, right? We can also combine this to a new type of formulation. We can say Q is equals to T1 minus T3 divided by the resistance of the wall. Do you remember the thermal resistance from undergraduate? So this is it, thermal resistance. So what are the assumptions? When you want to use the thermal resistance formulation, what are the assumptions we have to be able to make, right? There shouldn't be any heat generation. That's a very important. I see a lot of students make this mistake that to apply this resistance method to a problem that has heat generation. There shouldn't be any heat generation. Why is this the case? Because if we have heat generation, then we don't really have this formula anymore. We can't really apply this heat equation because here, this won't go to zero, right? Pretty simple. And it has to be a steady state. Let me write down the assumptions. A steady state, no heat generation, and one-dimensional. Okay. Well, how can we find this resistance? Of course, we have different types of resistance. We have conduction, convection, and radiation resistance. Right now, for these two walls, we are only looking at convection. So what is the resistance of convection? Or conduction, I'm sorry. We are only doing. So we are going to get thermal R of T, thermal resistance. Thermal resistance of conduction is equals to L divided by K. Okay? So for this wall 1, thermal resistance is L1 divided by K1. For this wall 2, thermal resistance is L2 divided by K2. Okay. Any questions so far?
Yeah.
Yes.
Would you not have to include the area in that formula there with the resistance in it?
I'm sorry, the area should be included either here or inside the resistance. That doesn't really matter. But if you wanted to include the area, if you wanted to have the non-area version, you should have L divided by Ka, right? Let's actually include the area here.
But if it were 2 or 3-dimensional, well, I guess you couldn't use resistance then anyways.
No, 2-dimensional, no. Radial, spherical, yes. 2-dimensional, no. Okay, so let's rewrite this Q using this thermal resistance. Q is equals to T1 minus T3 divided by L1. Or let me ask you this. So this resistance here, we have 1R1, R2. How should we combine these two resistances to get a total resistance for this wall? It is series, right? When it is series, you should just simply add the resistances. So R total is equals to R1 plus R2. And here we have R total in the denominator, here. So I'm going to get L1 divided by Ka, K1A, plus L2, K2A. You can also apply this to a case of one-dimensional convection. What does that mean? Let's say you have a wall, and you have convection outside of this wall. This wall, let's say this wall is exposed to some sort of an airflow or water flow, right? Instead of a constant temperature. One side we have constant temperature, on the other side we have airflow. And also, we can do the same analysis with radiation. Whenever you see this sign, This is telling you that you have radiation present. Whenever you have this sign, this tells you that you have convection present. Okay? As long as you can safely assume that this is a one-dimensional heat transfer, you can apply the thermal resistance formula. The only thing that is different here when you are including convection is the resistance of convection, which is 1 divided by H multiplied by A. And if you have radiation, you are going to have 1 divided by HR multiplied by A. Do we remember what HR was from the previous lectures? If you recall, we linearized the radiation heat transfer, right? It came up with this HR, which is the radiation heat transfer coefficient. It was sigma epsilon T plus T surrounding multiplied by T squared plus T surrounding squared, right? So we have all of the resistances. For this case, let's remove the radiation. For this case, total heat rate from this point to somewhere inside your airflow is going to be equal to what? It is delta T over R, right? What is the delta T? What is R?
Delta T is the temperature difference.
Which temperatures?
T infinity minus T.
T1 minus T infinity, right? Because we are not we have incorporated the negative sign. Divided by, what is R here?
I don't know.
R1 plus R2, which is L1 K1A plus 1 over HA, right? Okay. And we're going to come back to this and solve a couple of examples. But do we have anyone in class who doesn't remember thermal resistance at all? No, that's good. Okay, so let's move on a little bit. When it comes to thermal resistances, we have this new parameter called the overall heat transfer coefficient, U. This parameter will be very useful when we are talking about heat exchangers. And it's very useful in heat exchangers in general. So let's say you have a system of 4-layered wall. You have convection on one side, and you have radiation on the other side. Q here is going to be delta T divided by R1, R2, R3, R5, whatever. How many R's you have? As many R's as you have, right? Delta R, or I'm sorry, sigma R, right? And then this is equals to UA delta T. When you set these two equal to each other, you can calculate this U, which is the overall heat transfer coefficient. So if you were asked to find the overall heat transfer coefficient, just solve this regularly as you would. Then you set it equal to UA delta T to find the overall heat transfer coefficient. But so far we have only talked about the series resistances, right? So these resistances are in series with each other. What if they are parallel to each other? This type of wall. Let's say you have heat coming instead of this orientation, this axis. Heat is transferring from here to here, right? So it is essentially seeing this wall as a parallel thermal resistance. What is the difference here? The only difference is the orientation of your wall, right? Or the direction of heat transfer. Nothing else is different. And how would we find the total heat transfer here? Total thermal resistance. Yes, exactly. So if you have two, you can apply that equation. But the general equation is like this. 1 divided by R total is equals to 1 divided by R. R1 plus 1 divided by R2. right? If you had 3, then 1 divided by R3. If you had like infinite layers, 1 divided by R of n, right? Okay, so we understand the series thermal resistance, we understand the parallel. What if you have a combination of the two? How should we deal with this type of problem?
Find the total resistance for the middle part, right?
Pardon me?
I was saying, find the total resistance for like the middle tube.
Yeah, so what if I ask you to find the total resistance? Oh, find it, you were giving me the solution.
Yeah.
The question is, find the total resistance for this whole thing. And Daniel was giving us the answer.
Yeah, do the parallel, find the total for the parallel and then do it like a series.
So parallel in the middle, parallel, and the rest of it is series. Is this true? Do we all agree that this is true? Yes. Can we safely assume that heat transfer here is one-dimensional? Because the idea was one-dimensional heat transfer needs to have uniform temperature on all sides, right? Here, we have different walls. We can't really assume that we have uniform temperature here and here. So what should we do?
Think that it's how can I say? It's one dimensional between those two.
Between these two?
Yes. And when we I can't explain.
When you find the total,
Yeah, when you find the total, then it's one dimensional in X direction.
which is the same thing as Daniel said. So you agree with Daniel, right?
Yes, so it's one dimension.
Okay. Do you have any other ideas? Do you have anyone who disagrees with these two gentlemen? No, we all agree. So that assumption only works when you have something called the parallel isotherms. Do we know what an isotherm is? Exactly. So it's isotherm is a curve that has a constant temperature. So a temperature contour is a combination of different isotherms. So for one is you have 273, for other one is you have 283, 293, and so on and so forth, right? On this line you have constant temperature. So if you were told that this case is a case of a parallel isotherm, which is essentially telling you that here on these lines we have isotherms. So temperature here is the same as temperature here. Temperature here is the same as temperature here, right? Then yes, you should find the total here based on the parallel assumption, and then treat the whole thing as series. But if that was not the case, because this is a huge assumption, right? We have two composites. It's a two-layer wall. Obviously, temperature in reality is not the same, unless the conductivities are very close to each other, right? If that was the case, we can make another assumption, and that assumption is parallel adiabats. What is an adiabat? Adiabat is a line from which there is no heat transfer. So we have heat moving tangent to it, but no heat can cross it. This is called an adiabat, right? Like an insulation is an adiabat. There won't be any heat transfer normal to this wall, right? So if we can make that adiabat assumption, this essentially means that there is no heat transfer in these directions, right? What does this mean? This means you can treat this wall as two walls that are parallel to each other. So I can cut this wall from the middle, treat these as series, and treat these as series. Does this make sense? So two assumptions. Whenever you get to a composite wall problem, you should ask this, ask what is the assumption here. Or if you were to design a composite wall and you wanted to find the heat transfer rate through it, you have to make a sensical assumption, of course.
So would it be wrong what we were doing initially, like solve for parallel?
No. It really depends on the assumption, right? If the assumption is parallel isotherm, then yeah, Daniel's and Human's solutions was correct, right? But if you have a parallel adiabat assumption, then that solution is not correct. Does it make sense? Okay.
So the answers are the same, or?
The answer, if you have a parallel adiabat assumption, the answer is not going to be the same as parallel isotherm. So if you were designing this type of wall, right, you have to make the correct assumption for your calculations, right? And it's not that hard to investigate which assumption is more correct, right? You can just make the assumption, compare it to your experimental results, which is essentially, by experimental result, I mean just temperature measurement on the two sides, right? And then find the final better assumption, yes.
Sir, in the parallel adiabat assumption, what is the total R of it? Because they are not parallel, so like we can't take the series and then parallel.
So this, let's say this is part 1, part 2, part 3, part 4. And let's call this side of it 1A, 1B, right? 4A, 4B. These are series.
Yes.
So our total of 1 is RA1 plus R2 plus R4A, A1A. Our total of 2 is R1B, R3, R4B. And then these two are parallel. So your total R is going to be 1 over R total 1 plus R total 2. Okay? There is one thing in your notes that it is essentially an extension of this discussion, that they treat the heat rate with this essentially, they use this equation to find the total heat rate. S multiplied by your conductivity multiplied by T1 minus T2. This S is a new parameter called shape factor and is defined as 1 over total R multiplied by K. It's essentially the same thing as resistance, just the reverse of it. And we have two tables that is also included in the lecture notes that gives you the S, the shape factor for different configurations. So make sure to go there, or make sure to have these actually during an exam if you need them. Let's move on to the fins. And then we'll come back and solve two example problems. Yes?
Are these in the note you uploaded on Blackboard?
I haven't uploaded these yet. I will upload them. Lecture notes. That's chapter 2 lecture notes. Fins or extended surfaces. What are fins? Do you have anyone who wants to give an answer to what are fins?
Don't they like increase the surface area so you have more?
So essentially, fins are extensions to your surfaces that whole job is to extend the surface area, the heat transfer surface area, right? And when you extend the heat transfer surface area, what are we doing? We are essentially increasing the total heat transfer rate, because total heat transfer rate is a direct function of your surface area. And in general, fins look like this. Let's say that you have this wall, and I'm pretty sure you have seen this representation of fins many times. Let's say you have this wall. This is a fin, an extension of your surface. Again, here we have the same assumptions. This one-dimensional heat transfer, no heat generation inside, and so on and so forth. But there is one difference compared to regular one-dimensional heat transfer. And the difference is that this surface is exposed to convection, right? All around it, you either have some sort of fluid, some sort of a liquid or air, right? Or some sort of gas, right? Which means that you definitely are going to have convection, which means that it is going to be a little more complicated to deal with compared to the regular one-dimensional heat transfer. So how can we deal with the fin, heat transfer inside the fin? Again, the first thing you do, as we always do when we derive an equation, is we take a small element of this fin surface. And the assumption here is that this area, cross-section area, is changing. Okay, so let's write an energy balance for this. What is the energy coming in? QA, right? That's true. Conduction is true, but I was looking for QA. So Q double prime X multiplied by the cross-sectional area. What is the energy going out? It is going to be the same thing as before. Q double prime A, AC, DDX, Q double prime X, AC, multiplied by dx. So this part, it is equals to 0 because there is no changes with time, right? This part of it, E dot of CV, was the rate of change of energy inside the control volume over time. It's still one-dimensional, steady state conduction. So this part of it is 0. And then, what else do we have? Convection. How should I include convection here?
Boundary function.
Which boundary? This boundary? This boundary? Are you talking about this? Okay, so it's essentially a boundary of the control volume, not boundary of the geometry, right? Okay, that's true. So how much convection we have from that boundary? This is plus sign. How much convection do we have from that boundary? What is the total convection from that boundary? H delta T is going to give us the heat flux of convection, right? Which is this delta T is the temperature of that surface minus T infinity. Heat flux. But we are looking for total heat rate. So we have to multiply it by some sort of an area, right? What is the area here? The area is the area of the surface of the control volume, right? And we are going to say just a derivative of area, a small area, surface area. And this convection is actually part of the energy going out of the system, right? Energy equation is not a vector equation, so energy going out in different directions can be combined with each other, right? It is not a force equation. So plus this. So your final equation is going to be equal to E dot in equals to E dot out, which is Q double prime X A of C equals to Q double prime X A of C plus the changes based on the Taylor series. You remember this discussion. A of C dx plus H das T minus T infinity. Okay. These parts cancel out. Then we can rewrite the equation as d dx okay. Let's divide this whole thing by a dx. Let's see what happens. This, you can drop this. When you divide this by dx, this is equals to 0. d dx q double prime a of c plus h dA dx, so the derivative of the surface area with respect to x, t minus t in, this is t infinity, I'm sorry, t infinity.
Wasn't that dx just a change in length though, not the derivative? I guess now that you've divided it, it's become.
Yeah. I mean, a derivative is always a small change in a direction.
Yeah, that makes sense.
Okay, so, and we can, this is governed by the conduction equation again, so we can bring that out, negative k partial t partial x, but we only have temperature depending on the x here, so we can change this to absolute derivative k dt dx. This is equals to 0. What is the next step here? I'm going to replace q double prime of x with k dt dx. What is the next step here? And I guess I've messed up a negative sign here. This should be a negative sign. If you go back to your, this should end up being a negative sign. No. No, I want to take the derivative. I want to simplify this or expand this. What would be the expansion of d dx of q double prime x ac? Anyone?
With dt dx and then with AC because AC is different.
AC is changing with x, right? Is a function of x. So we cannot just take this out of the integral. That is correct. So d dx, this is essentially the same as d dx of y multiplied by z, right? It's going to be dy dx multiplied by z plus dz dx multiplied by y. This is what you were referring to, right? Okay, so let's do this. Both of these are changing with this, changing with x. So I'm just substituting this negative k dt dx for q double prime of x and taking the integral, taking the derivative. It is going to be ac negative k d squared t dx squared plus dt dx, and again negative k is multiplied here, multiplied by dac dx minus h das dx t minus t infinity equals to 0. Is this clear? Okay. So let's divide this whole thing by AC and negative k. We are going to end up with d squared t dx squared plus 1 over AC dt dx multiplied by dac dx plus or it is a minus sign. So this was one mistake again. This was correct. I'm sorry. This is a minus sign because we are dividing it by negative sign. I'm sorry. Minuses and pluses always get mixed up. H divided by K das dx multiplied by t minus t infinity equals to 0. So this is going to be the general governing equation of a fin. Any questions? What happened here? Where is the confusion?
The last part, the last part.
This, so from here to here? Okay. So we divided or we multiplied this by a negative k AC, which means that this cancels out. This k cancels out, and this is going to become 1 divided by AC. And here we are going to get k AC and a negative sign. And the left hand side is 0, so we are going to keep having 0. General fin equation. Let's solve an example. We are going to solve a fin example first, and then we're gonna go back and solve another example with the thermal resistance. Let's say we have a rectangular fin. Okay. And it's a uniform cross-sectional area and a length L. The fin base temperature is given to us. Let's call it T of B. And we are going to assume that fin tip has adiabatic condition. We are asked to find the heat rate or temperature distribution over the fin T of X and the heat rate of the fin. Of course, you want to start from the governing equation, right? How can we simplify this governing equation? Changing area is 0, right? Because it's a uniform cross section. So this second part goes to 0 for this specific problem. So the governing equation for this problem is going to be equal to d squared t over dx squared minus 1 over AC h divided by k das dx t minus t infinity.
What is that second unknown number solving for? What is that symbol?
Q of fin. Q of F. Okay, so a couple of things that we need to introduce here when it comes to fins. For fins, we usually introduce two new parameters. One is theta, which is equals to temperature at any point of the fin minus T infinity. And one is m squared, which is HP, and this P stands for perimeter. How do you write perimeter? I think this is an I, right?
Yeah, it's PER.
PER, is this it?
Yes.
You understand what I'm talking about, the perimeter of something, right? Divided by KA. These are the two new variables we introduce in fins for the sake of simplicity. How is this going to change our formula, governing equation? Let's look at this. D squared dx squared, and we want to find the theta squared of theta dx squared. We said theta is t minus to infinity dx squared, which is going to be equal to dx squared t dx squared minus d squared t infinity dx squared. What is this derivative? 0, because it's just a number, right? T infinity doesn't change, it's just a number. So d squared of theta is equals to d squared of t. Nothing changes there. What about t minus t infinity? It's literally the definition of theta, so we have to just replace this with theta. So let's rewrite the governing equation based on this new theta parameter. 1 minus 1 over AC, h divided by k multiplied by theta multiplied by das dx. Let's look at this. This is a uniform cross-section, right? We're dealing with a uniform cross-section. So for a uniform cross-section, we can expand this to the whole fin, right? If you do that, you're essentially dealing with AS divided by L. What is AS divided by L? The perimeter of the fin. So I'm going to replace this with the perimeter, which tells us this is also m squared. So your fin, rectangular cross, or a uniform cross-section fin's equation is going to look like this. We are already past time, so we are going to come back to this on Thursday. Because we had to move a little faster. That is all right, though. Is there any questions? Did we all follow what happened? A little bit. That's all right. You can always go back and you can always come to my office and ask questions if you have it.